Hi, Mel's. Welcome in. Just working on getting the recording stuff set up. That's always the hard part. Alright, good. Looks like our monitoring computer is back online. Excellent. Okay, so just wait for the ads to roll through and then we should be good to go. I know, Martin. Streaming and recording at the same time is weird. Luckily, Twitch does most of it automatically for us, so that's a bonus. Alright, so most of us should be back. Hello, welcome in. My name is Penn Center. Today we're kicking off the very first presentation for the Linear Algebra Reading Group, the Friedberg Reading Group. If you haven't done so already, you can head over into Discord. Oh, it's true. If you haven't done so already, you can head over into Discord. You can find all of the relevant links to other servers through the elements. Or you can DM me over there as well, and I can get you into the particular servers that you need to. The materials are being hosted in Simple Server right now, and the Mathematics Discord server has actually invited us to do our first presentation over there. So we'll actually be heading over into the Mathematics Discord server. You can find the link under notifications in the elements to get to the Mathematics Discord server. And we'll be heading over there, and we'll be listening to Mina today talk about vector spaces and subspaces. Everything has been... what's the word I'm looking for? I've kind of disabled everything today, so there are no pop-ups, there are no annoyances. We're going to put our full focus on listening to our speaker today and see what Mina has to bring along with regard to vector spaces and subspaces. So we might be a couple minutes out yet, but we'll pop into the mathematics server and make sure that everyone is looking okay. All right, everything is looking good on Twitch side.
I think we can start then if you're ready. I will go off.
Yeah, whenever you're ready, Mina.
Okay. I will just pop out your Twitch chat, because if someone said anything, I could see it also. Before we start, do you know how to pop out Discord chat? Because I'll be in OneNote, but I couldn't see the chat of Discord. I could split screen.
I can monitor Discord chat for you.
Okay. Well, hello everybody in Discord and in Penn Center Twitch. I would talk about the basic sections. We will give overview and old stuff about vectors, and in the later section we will talk about what is a vector space and what is a subspace. I would like to give you introduction about me. I'm Mina, a first year student, uh, like an undergrad, and we doing like some very wonderful, perfect reading groups in like simple group server. I hope like give it a look. And this is a linear algebra group in like Friedberg book. And if you didn't like follow up like last week and you didn't see like what is this reading group, check it out. uh, it will be good if you like follow up with us. I would start like uh, the very cliche introduction. What is an old definition of a vector? You hear out from like in high school, which is like the old definition is you could type it like yeah, a direction and a magnitude as something. Old definition of like vector, something like that. So two main things, that is a magnitude and a direction. And we will go over an overview in like the normal Euclidean uh, space, or like how it work in adding some vector and how we scale them to like remembers, and like if we have like something like this, we call it R2. um, I will go in what is the meaning of R2, but it's something that has like two components, which is both are real. For that, a vector like V would look like that. We go from the origin, and we would call it V, and sometimes we put something to point out that is this is a vector, like a bar on it. Is this good? Then, if we want to add some vectors like V and U, there's some good rule, which is a parallelogram rule. If you like, this is U, this is V, then if we get like an image of V on the tail of U, we will get something like that. And this would be like U plus V. But this is the same as V plus U, because we could do the same thing. We can get the image of U and put it like that. And we see we will go to the same point in some kind. Is this clear for you? Like the notation is slash vic V, I think it would work. Something like that. I'm typing in Discord, by the way. No, I'm not talking. Okay. And
Good morning, Inian.
if
How are
we
you
want to
doing?
give it like algebraically, how we do it is if you point out how it's going. If we have like V has like V1 and V2, the values that has it, and U has U1 and U2, and if we add them, it would get us V1 plus U1, comma V2 plus U2. And this clearly u plus v is v plus u because these are like two real numbers, and in real numbers, numbers are commutative. For that, it is true. And why is this is the same thing as a parallelogram? If we break up what we have done in the parallelogram, I'll make it bigger to be to be more clear. If this is u and this is v, we know that is at the end of the parallelogram is like that. This x component is just the x component of the u, and you would see this the x component of the v is the same as this part. And the same thing about the y coordinate. For that, it's just adding uh, the entries order-wise. And when we talk about scaling, there's some another property that vector could have that we could scale it with some magnitude. It's like if we have some v like that, we could say there is some tv where t belongs to reals. Now, there's some definitions that the book gives, like what is two vectors are parallel is when we have like two non-zero vectors like u and v is non-zero vectors, and u is equal to tv where t is not is non-zero real number. Because if it is zero, it's any vector could be parallel to that, then u is parallel to v. I should like remove that. Remove that. I couldn't see this crochet. I can't. I have to like put it in front of me because if someone asks something, is it all good? I guess it's all good. Okay. Then, if we want to take what about this property, which is addition and multiplication, what properties that we got from we talking about like addition and multiplication? That we hope that our addition is commutative, associative has its additive identity, and the multiplication is exactly the same. We could see that there's identity element for multiplication. It could be associative in some kind, and there's distributive law. For that, we could write them down. Like those are the properties when we're talking like an addition and multiplication. For that, if something has these properties, we could um, give a glance. Oh, this is a very similar to what a vector is. And if we want to talk about spaces, and we will talk about space here, like 2D spaces and 3D spaces, if it's a line or it is like 2D or like a plane or a space, how we could write it as vectors. And let's write the properties we know that. Let's me write some introduction for every vector x, y, and z, and a, b scalars. We could see that x plus y is equal to y plus x. And if we done something like that, x plus y, we add them together at first, is exactly the same if we add y and z firstly, then we add x. And for there's like a zero vector, if we add it to x, it will point out x. And there's a more important one, that x has another vector, which is if we add it with it, it will give us the zero vector, which is, we would call it negative x. It's the inverse, additive inverse of that vector, which is the negative x, and we would get zero. And in multiplication, we would have something a little bit similar. 1 times x would get us 2x. And if we multiply a, b firstly, and then we multiply it as with a vector, is the same as if we multiply b with a vector, then we multiply it with a. And a could be distributive in the sum. And there's a similar sentence to that, which is if we have a plus b, which is a scalar, we would get ax plus bx. These properties is like something we should have seen from, like, this is addition, there is a multiplication. These are some things that I pointed out from those properties, something like that. And we want to reach is a general things, or not like something magnitude and direction, something I could check, then the thing I'm talking about is a vector. Because a magnitude and a direction is a little bit ambiguous to define what a vector is to mathematician. For that, we needed to like point out what properties we would see about vectors, which are those. Okay, let's go under there. If we have like some two-dimensional space, and I want to talk about line. It doesn't have to be 2D. It's just any space, and I want to talk about a line. And we have some point of origin, which is O, and point A, and point B. And I want to talk about this line as vectors, how I could do that. Well, we know that all vectors here are parallel to each other. Like, let's call there's a vector W here, which is, if we got this W and multiply it with T, will get us every vector in that line. But the idea here is this is not the origin. The A is not an origin. For that, we have to shift this from the origin with the vector that pointing out of A, which let's call it this AU. And we could call the vector from getting out from origin to be as a V. Is this clear? Check your audio and visual settings. So vector is like a normal mass, or there any abnormal things. Worked fine now, didn't change anything. Okay. 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 Is everything good for and people on Discord? Okay. Okay. Okay, you can hear me fine. Is there anything that's feel it, or you just didn't get it, or something like that? Everything is great. Okay, okay. We want to get what is this W, and clearly how to get this W is something like this V is something equal to U plus this T W thing. And this W thing is just P minus A, is like if we see this vector, which is the same as the vector in top, is just V minus U. For that, if we want to write a general formula about uh, what is the line we are talking about, we could say is just any vector in this line would be what a name we call it. X is U plus T times V minus U. And if we give some points as an example from the book, like example number 1, let A and B be points and have coordinates. And are the coordinates of A and B respectively. The endpoint, see, this is what we are doing here is we have another point as our origin. For that, we needed to move them firstly, then we will get our directional vector. Let me draw them to be more clear. If we have some point A, which negative 2, 0, and 1, and some B, let's make B here, some B, which 4, 5, and 3. And this is our origin. Then the C we are talking about is the same like W, as if we done this as a vector and this is as a vector, and we see the image. This is the point C he's talking about, which is to get the direction of this vector is just like this minus this. We'll get okay, and white and white, and it will not be clear. This 652, 4 minus 2, 5 minus 0, 3 minus 1 would give us 652, and we multiply with a factor because it's the all parallel to each other and just shift it with A. And there is a similar argument for talking about planes, but now we have two axes to talk about. Is like if you have axis like that and axis like that, and there's some vector I want to talk about, which is x. Then this point be A, this point be C, this point be P, and let's say the direction of this vector would be, let's remove the A, let's put it here to make it, and okay. I want to change the lenses to make it like, it could be like very small, like let's A be here and C be there, and it could go along the way, and B would be here. For that, if that's U and this is all this V, and there's some X's like Z, then we could write it as a sum of those two vectors. There's some vector like that, which would be TU, and some vector like that, which would be TV. For that, if we added the C minus the origin, which would get us the coordinates of C, and we add the TV, and we shouldn't have the same magnitude. I'm very sorry. it had to be like some S, because this is have some component and the other have another component, which would be cu. Then we could write any vector in the plane of this axis, which is an A and B, with a formula like that. And there is an example in the book. Uh, most of the stuff is, I guess it's very clear. For that, I want to go through a point which is not written in the book, but I guess it's very important for the upcoming section, which is, I think, the important section, and we will give it more time and think about the stuff in the later section more. For that, the concept that I want to introduce, I guess it's important, which is the Cartesian product. Well, you all familiar with what is a set? A set is a collection of some elements, and if we have some like two sets, yeah, okay, okay. We'll see is not TV plus CU, or or was it an identity? I don't get what's your question. Okay, was C not TV plus CU? Uh, yeah, yeah. No, no, no. C is not equal to TV plus X is equal to that. There is a vectors in X. We don't know what is X is. X is just vector here in this plane. And if we okay, let's give this, remove this. If we have like some three-dimensional space, something like that, and there's some plane, and there's C, and there is our point A and our point B. And we won't talk about vectors here in this plane. But to write vectors here, we have to point out that it's shifted up and up. For that, we have to plus the C, because the vector which is like that is not like that, it's just like that. For that, we C plus the vector we point out, we will get us the actual vector, which is from the origin of our system and we are talking about. Okay. Let's okay. Why I get I pressed the home button. Cartesian. I hope I guess I spelled it wrong, but you got it. Cartesian product. Well, if we have some set A and another set B, we could define another set called AXB, which has the elements of A and the elements in B as an one element, which is, let's call all, I will write the definition like that. A, B, where A was like such that A is in A and B is in the bigger B, which is the set. Okay, I have to. But here the ordering does matter. Like A comma B is not equal to B comma A. For we're talking about Cartesian product, we care about what is an order is. For that, this is a pair of elements from A and B. For that, this set just has all the order pairs of elements A and B. And this is very good because we could do something like that and have two elements, like let's call X and Y, where X and Y is in R. And this is very similar to an R2 vector would be. For that, we like make it make some notation. This is just our superscript 2. It's like a shortcut to not just R X R, because we could make another X to the set, because this is now a new set. Why we don't do a product across another set? If you have like A X P, this is a new set. Why we don't cross it with C? We could do that, and we got something to a set with elements like would look like that: A and B, other parentheses, A, C, and C, where A is in A, B is in B, and C is in C. However, if we see this set, this is not the same as this. And this, to make it clear, an element like that would be looking like a parentheses B, C. For that, they are not equal. But however, every element here has an image there. For that, we could do some magic in some kind, and we say it doesn't matter, and we could say A, XP, XC, and those have sets like pairs with pairs of something like that. But it's not rigorous enough. But this is like we could do if I have an object in there, I could just map it to the other object, and this other object is the same as other object. For that, it's not ambiguous to write something like that. However, in actually this thing is not totally the up thing. Okay, but yeah, for the shortcut, we could talk about something like that. Okay, is this clear? Yeah, I want like you feel comfortable when you seeing something like that. For that, we could do something like R X R X R X R X R. For that, we could talk about something like Rn, which is just R X R X R n times. There's a fancy way to talk about this object and this this object and this one, but it's not important. And an object like that, we could do any set with like X, and we do N, and we call it like an N tuple, a set with N tuple elements. Elements. What is going on, boys? Elements from X, where entries of this N tuple are from X. Entries the N tuple are from X. For that, Rn has an element like that: A1, A2, An, where it is in Rn, and any AI is in R, where I could go from 1 to N. Can you add R and R? Uh, there's it's not important to talk about something like that. I have seen this in our usually used for our subgroups that have similar structure to R. Direct sum of R and R are same as the product. Okay. Now I want to talk about some stuff. But this one would be in section 1.2, which is before we start, we could talk about addition, like if we talking about R. It's something like taking elements from R cross R and get an R. For that, an element would look like that, A and B, and would get us A plus B. Plus is just a function which take two elements, which is not a two elements, it's just a one element in an image of two elements in like order pair to this A plus B element in R. For that, we could write some stuff like that. Let's go into like the heat stuff. The first definition we would get from the book: a vector space V over a field F consists on two operation plus time is with some axiom. We will talk about the axiom
Video sensation.
now. Let's firstly, what is the two operation I'm talking about? I'm referring to this plus and this timers, and what is an axiom, and what is an F, or field. I'm gonna say. Well, when we talking about field, what is a field? Is something like a scalar, something like a real number, something like a complex number. For that, anytime I'm talking about field, just like replace it with a real number in your mind. And what is this two operation we are talking about? Plus is just defined to be if we are talking an element from V and another element from V, we're getting another element to V, which is a vector plus a vector, we get another vector. And this multiplication, we don't write it as a dot, actually, we write it like, take it up to like the vector is like, I don't know, could like write like some space or something like stick something is something like space, which is take a vector and which actually it's take field cross a vector and gives us a new vector, and here is a vector, which is the time is will be more clear if we like take a scalar A and a vector V. This is a smaller V, but would get us AV. And the plus is very clear. If we have like a vector V and vector W, it maps to V plus W. And why I wrote those, we could make them as an axiom, like plus the stick multiplication thing is closed. What I mean by closed, like if I add a vector plus a vector, I get a new vector in the set of vectors I'm talking about. And if I multiplied a field or a scalar to my vector, I got a new vector, which is closed, which is in my set of elements of vector. Some books take the closed property as an axiom. An axiom is just some stuff, axioms, is some stuff we, if there exist, we like define something. If there exists, then this is a vector. And what are these things? We will give an axiom. Is just the properties of vector we have seen in the section 1.1, which is commutative, associative, an identity element, an inverse element, all those good stuff. Okay. What is the first axiom? Well, the book is rated like VS1. Something to be clear is to differentiate about the vector space and the set of elements which has the vectors. Uh, and it will be more clear about what is that and what is that. Like the set of vectors and the vector space is totally different thing. The vector space is like I don't know if it's the right word or not, but and like algebraic structures that has a set and two operations, but the vector is just the vectors, the set of the vectors. Uh, the vector space has additional elements of the operations. Okay, and sometimes books write the both things as V, but that's sometimes unclear what do you mean about V. Okay. But I will be clear when I talk about a set of elements or a vector space, I'll be clear what V I'm talking about. Okay. Uh, for all x, y, z, we are in our vectors, and a, b in our field, we have some axioms we want to check. The first one is that x plus y is exactly 1 plus x. And the second axiom, which is the associative, is the typical things we need for an addition. Are you gonna say something like that? But it doesn't have to. It's something like that. X plus y plus z. And the third axiom, we have an identity element or a vector O. This zero is not the same zero we are talking about. Like when I see plus 0, then this assumes the 0 is a vector. Because it doesn't make a meaningful way if I'm talking a 0 in a field or 0 is like real number, because we can't add a scalar with a vector. This doesn't mean a thing for that. 0 here is a vector. I should have like there exists and 0 element, which makes something like that. And the fourth axiom is like we want an inverse is what we want. Like there's exists a negative x vector where we add x and negative x, or the inverse of x, the additive inverse of x, we got the 0 vector. And axiom 5 is with multiplication. If we have two elements from the field and multiplied with a vector, we got a b x, which we multiplied b with x, then we multiplied a. And the multiplication here is totally different than the multiplication there. The multiplication here is the multiplication operation over fields. The multiplication here is the multiplication operation we already defined. Since this is a field, and field like reals, complex number, is already has plus and times in them. I'll give like a very short explanation what field is. It's something like has plus and times with inverses in them, an identity element for both the plus and the multiplication. For that, you could find like an inverse multiplication is real, an inverse sum, additive inverse in the real also, and the distributive law is exists, and identity element for sure. VS6, which is 1, get us x. which is there's an element from the field when we multiply it with a vector. There's X. I'm sure I'm trying to shorten the axioms, but I have to write there is exists this element. We write in the top for every for that we have to writing like there exists this element. We could find it, and V7 is like if you have a scalar and x plus y, we could distribute the A, and VS8 is something similar, which is A plus B with X, AX plus AY. Then what should I do to check if a something uh, is a vector space or not? Firstly, we need to define something. What's the set I'm working with? The plus operation, the multiplication operation. Then check the axioms in this operation is true. Then what I should do is to define the set, define the plus operation as a multiplication, then prove that axioms holds in those definitions that I have give. Then what I'm talking about is a vector space, and we could go through examples now. If someone has some examples, we could try. Okay. Uh, should What's the difference between a vector space and a field? I guess I have okay. This is was there's a difference thing, but a big difference. And I'm reading the Discord chat if someone wants to point out some question I have to talk about. I don't know the street, so I'm trying to follow. Basically, I feel there's some growth thing was what I wrote. Oh, okay, I have written B. This is a typo. By. Okay. Okay. Let's give some examples from the book. The first, I will give the first example, and I'll try to see if you could point out another examples. If we talk about the set of functions, which we will denote as something like that, which take as points from or elements from S and point out to our field, which is the if, the small f, which is in this very big if, we'd do something like that. We'll take an element from S and point out to the field. This is a vector space. Let's define some. What is addition and what is multiplication? Then check our axiom. Well, clearly, if we have some f and g in the set of this function, S and the field, we'll see that we could define addition like that. F of x plus g of x. And scalar multiplication to this x to be just multiplying to the output for all x's, and here for all x's. Where x's, this post x's are ns. I should have like ns. There's like two questions that, or some multiple question I guess you would have. Why we have chosen S to be anything, and another thing, why we chosen the output to be F, has to be F, because we want to make C times F defined easily. For that, if this is a field element and C is already a field in the element, C is already in the F, then this is already defined because an element in the field and an element in the field are real number and real number. we are sure we could multiply it, which with each other, and adding two real numbers and is already defined for that. The output has to be a field, and in our field code, this easily would verify addition and multiplication in what we are talking about. But the input doesn't has to be a field. Could be anything. It could be uh, like red balls and blue balls that I have in the bag. I like get out some random ball. I put it in the function. This is output two, and this is naming that I put in my balls or something like that. And we could check that axioms are true for that if we check an identity element, which is uh, in adding, which is a zero function, which would be just the zero. And if I want to talk about uh, the inverse of x, it will be exist, which is negative of f of x, and negative of f of x is just the inverse of this real number, an example, and this is already exists for that. I could just write it as that, and I could check if I added fx plus the negative of fx, this would get me a zero. Yeah, s could be anything that has something. S can be have nothing. S can't be the empty set. For that, S has to be the non-empty set. Any non-empty set would be good. Uh, we could give some examples for functions like that if someone could point out what functions that take anything and point out a real number, for example. And I only checked the zero element and the negative because the eight axioms or the other eight axioms rather than those two is just straightforward got from what we are calling the scaling property from the operation, because this is already defined and this is already defined in the rear, and distributive law and scaling and identity element of multiplication is already in our field. For that, we doesn't need to justify the other axiom. For clear to say that this is not random, or at least yes, if axioms are vectors. If f is a vector, does this make the stuff an s vectors not necessary, or what? We could give some examples about some functions which is mapped from reals to reals, which is the polynomials. And we will talk about the set of f, which is the polynomials with coefficients of the field and it's defined over field f. What I mean by over, which is this is a vector space and it's over f, because we will talk about, we will not talk like, yeah, we multiply it or scaling it with the field, or we just write over f, like shortcut our writing. Then if we have some function with some a n x n, a n minus 1, a x n minus 1, to a1 x plus a naught. This is an element of b of f. And the bf has all polynomials with all degrees, not necessarily at most some degree. No, it has all degrees of polynomial. And what I mean by degree is what is like the most power I have in x's, which is here is in n, for that a degree of x is just n. F is n. And if we have the element which is 0, we will define it as having a degree -1. If would be would have degree -1. While if x equals some constant rather than 0, then this would be degree 0. Like f is equal to c and c is not equal to 0, then the degree of f would be 0. Let's define how we add polynomials. If we have some f like that, a n x n plus a n minus 1 x minus 1 to a1 x plus a naught, another g, which is some bm and xn and am minus 1, p bm minus 1 x minus 1 plus plus p1 x plus p naught. What we could do is that we could write g of x as the same order of f. F is like the order of g is less than the order of f, or the degree. Then we could just write that b m plus 1 and b m plus 2 just pn is just equal to 0. And we could write g with the same, in some kinds in the same order, and just add each a to b, and like that we defined our addition like that. For that, and f plus g over x would be an plus bn of xn and an minus 1 bn minus 1 xn plus a naught plus b naught. Well, we have our plus operation defined, and we need the scalar multiplication already defined. We want to make sure if the c is already in our field. Because, for example, if I have real valued, or what I want to say, like polynomials with real valued coefficients, if I multiply it with a field which is complex number, we will get out of our vectors. And we have to make sure that when I multiply, I don't get out of our vectors, And for that, I have to make sure that C is already the same coefficients as our coefficient of the polynomial. For that, we just make CAN xn plus CAN minus 1 x minus 1 plus dot 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 plus CA naught. And those two things, those two operation is closed under addition and multiplication. We see that f plus g is just another polynomial, and cf is already another polynomial in our set. And we already defined our zero element, which is if x equal to 0. And we could check that the negative or the inverse of f uh, is already existing. Uh, if we see what is the negative of x is, we would define like the negative coefficients of all the function, which is negative an xn plus negative an minus 2 minus 1, sorry, xn minus 1 dot dot 2 minus a naught. For that, we have our inverse, and those are main things that we want to check out. And b of x or b of f, sorry, is a vector space if we follow the other axioms. We won't talk about the matrices, which is has some number of rows, number of columns, and has entries in some field. I have to check out what's going on in Discord because I haven't been so long to look in the chat. Or like I think it's just sorry. Okay. If we have some set of matrices, we would call it M of like rows n times M, and has our entries in. Sometimes it's just real, and we will take it for the field. And a matrix is just an array of. It would look like a matrix would look as something like that: A1, 1, and A1, 2, A1, 3, dot, 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 A1, 2, M. Then this would go through A2, 1, A3, 1, and dot, 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 AN1. And we could get all the entries as something like that. For that, it's just an array of numbers, and those numbers are in our field, for example, or real numbers or complex numbers. For that, when I talk about this set M with nxm, to not confuse which is rows and columns, I'm not very good at English. For that, the first time thought that the column is n because it's as the first. For that, I checked out that is the opposite. For that, what is in my mind like C is before R, then it should be in the opposite. For that, M should be the columns, not the opposite. For that, what I do is I make them the opposite. C should be go first, but it doesn't because English is bad. Then M has to be the columns. I just will drink water. Then if I want to talk about any entry in my matrix, something like A, I, J. This means that this entry is in the i's row and in the j's column. I'th row and j's column. And I goes all one, two, um, n, and j goes one, two, n. This is clear? Just check. uh, and if we want to talk about entry in the diagonals, if a I j and I is equal to j, then this entry has to be in the diagonal. And mostly, this is we are talking about some square matrix. I don't know if it's in general it's a diagonal entry, because if we have matrix like that, 2, 3, 4, 1, 5, 7, the diagonal entries would be 2 and 5. Because here is this is A11 and this is A22. But mostly when we're talking about the diagonal, we check that it's the same rows with the same columns. And a zero matrix is just a matrix with zero entries. 0, 0, 0, 0. And in the book, if I want to talk about matrix A, and I want to talk exactly about an entry in this matrix, I will just talk about Aij, and I is my row and J is my column, and it would be enough for me. For that, this is entry in matrix A with I's row and J's column. Then, if we want to define an addition and multiplication in those matrices, we're gonna use a formula for each entry. To summarize all this, what we do is that we defined about matrix A, and then we took, hey, if we have A plus B, this is a matrix. I want to talk about this entry of the matrix. It would be just adding the same entry of A and add it to B. Then this is the additions that I want to define. And the same thing for scaling. CA is a matrix, but I want to take the entry in the CA, which is just take the entry of the all day and multiply it with this entry. And if we want to take some examples of this 2, 3, 1, 5, and we add it to 0, 1, 0, 1, it would be add each entry with the entry that going like the image of it and the other side, which would be 3 and 1 and 6. And the multiplication is something similar. If we take the same matrix up there, I guess I could multiply, which is 4, 6, 2, and 10. Then we have an addition, we have an scaling. Why don't she check axiom, is it work or not? Then the main thing we should check, is it close our addition? Is it close our multiplication? We have done this. It's close an addition and multiplication. Then we have to check, is it Commutative, I guess so, because A plus B, all ij, is just equal to A ij plus B ij. And this is our real numbers, because that I could flip them. It's not the real number, it's an element in the field, but I just give an example. That's our real numbers. Make it easier. A ij, A would flip them like that, and I like take the definition I make for addition, for that p plus a works. And I can do the same thing for associative rule. And if I want to add a to the identity, which is vector with all zeros, is easy to check, is true also. Aij plus 0ij, which is a. In the examination, it seemed like the rows and columns were the other way around. No, okay, maybe not. I just okay. This is what book shows. Mina is Arabic, so sometimes we put in M instead. Well, yeah, I like to put in at first, but it doesn't matter. You just have to remember that the sum that goes at first is 0. Okay, and we are sure that all axioms is true, because if you multiply it with 1, it would work. If you want to check scaling properties, does it work, which is the associative kind of, as the associative kind of what I'm talking about, which is a b v a b v. This is I call associative kind of. So the associative kind of axiom is work, and distributive work. For that, the matrix works as an a vector space, which is n times m or m times n, doesn't matter, but you have to, if all the matrix has the same rows and columns in your set, you can't have different rows and columns, because that you can't add them, because how you could add like a 2 by 2 matrix with 2 times 1 matrix, which is a vector. You can't add them up. For that, you have to check that rows and columns are equal. Then you could define how to add them and how to multiply them, and you find them. That is are closed. Is this clear? Are just addresses in the matrix. Number is always 0. It's not really that confusing, but I'm just better. Okay. I will continue. For that, we could say that m n times m over our field is a vector space, but you have to be sure if it's a vector space over f, because if we have a matrix with real coefficient and I make it over complex, it will mess up things and it will not be closed, because the entries will be complex, and if the entry is complex, it's not in our set now, and now it's not closed. Let's check some properties, which is very important, but we have to prove our very first theorem of the book. But I would check that I haven't missed anything. Okay. Just some additional examples before going to the theorem. Okay, let's just check them. If we have some, let's say, let we make some like pair with a1, a2. All the thing we are talking about is like in something like S, and a1 and a2 could be something in like it could be R. Let's make it R. It's just R2. Okay. And then let's define addition, but differently now, like that. If we have A1, like, and A2, and I want to add it with B1, B2, I would define it differently now. A1 plus B1, A2 minus B2. And I would make the scaling is the same. Have A1 plus A2, no, what, comma, A2 is just find to be CA1 and C2. The first question, why doesn't this hold? Well, the commutative property doesn't hold. For that, we could check if this is A plus B doesn't equal to B plus A. And we could easily check that for that this is the thing we have written up there. And this would be A1 plus B1, but now it would be B2 minus A2. And if we would remember, the second entry here was A2 minus B2, which is clearly not true for all A's and B's. For that, it's not a vector space. For that, we have to be clear about how we define addition and multiplication. Then we check if axioms are true. For that, we see this set could be a vector space or not over our field. Okay. For that, this is not a vector space under this operation. This operation, what will we call it? Bad plus bad. Well, I should have written it like that, bad. Which is the bad plus. It's a bad plus operation. For that, R isn't a vector space if we define addition like that. Okay. Let's go through the first theorem that I wanted to get into. The theorem says if we have some vectors, let x and y and z be vectors, then x plus z equal thing y plus z, implying that x equal to y. To prove something like that, if we have this x, we know from the axiom of the zero identity is we could write it like that because it doesn't matter. And since we could write it like that, zero is just a sum of two identity inverses. For that, we could write it as z plus or negative z. And with associative rule, we could write x plus z like that plus or negative z. And this clearly is this. For that, we could just put this instead. Y plus z plus or negative z. Then y plus with associative rule, we change this again. Plus our zero vector is just y. This is a very important rule because we will prove a lot of things with it. Is this proof is clear? Okay. I guess it's clear because why can't we subtract z from both sides? We don't know how to do that because we we to do the things that subtract z from both sides, we have to prove it first. Okay, and we didn't just prove that is this thing is, it could go like that and it could go like that too, but let's make it as just goes this way now. But this is a very important theorem because it's just not only saying that we could canceling these. That is, if I want to talk about x plus y equal z, and I know what x is and z is, but I don't know what y is a unique element, and this is come from the theorem 1.1. And if we want to check why is that true, let's say there is another y. Assume there exists some another vector y dash, uh, which acts the same, which is x plus y dash is equal to z. And we assume not just that y dash doing this, that y is doesn't equal to y dash. There's two vectors that make this true, but it's not the same. Then x plus y dash is clearly x plus y. But from theorem 1.1, we could say, well, y has to equal y dash, then it's a contradiction. Since a contradiction, y has to be unique, or has to be a one element in our vector, a one solution to this equation. Okay. For that, it's a very huge, not a huge, important statement to say. It's this theorem 1.1. Let's see what I should talk about now. Controversy. Okay. Let's prove something, that is, we have only one zero vector in our vector space. Okay. To prove something like that, we will do something similar, which is, we'll assume there's another zero. I will do the same kind of contradiction proof because it works. Zero dash, where it's not the same zero, which is already defined, and it works the same as our zeros, like a0 dash. And we easily could do like x plus 0 is just x, which just x plus 0 dash, and we could see that 0 has to equal our 0 dash, and we can create our contradiction. And this is clear. This is from theorem 1.1. Then we want to check that each vector has only one additive inverse in our vector space. There's no two additive inverse in our vector space. To do something like that, we will do the same exact thing. Let's assume new negative x dash. I want to x note. Let's do something like that, where x plus negative x naught is equal to 0. And we find that x plus negative x is just equal to x plus negative x naught, because they both equal to 0, and our negative x should equal to the negative x naught. It's unique. For that, what we have reached is the uniqueness of solving
Yeah,
this,
so Anders, with regards to
this type of
with
equation,
regards to the music,
the
there's like a
uniqueness of
little button
exactly
right
zero.
down
Have
here
zero,
that I had
only
to press
zero
to mute
vector,
the
and
music.
we have only one additive
So
inverse
provided you can
in
hear
our
me now,
vector
that's
space.
what I would suggest. Just seeing if you can mute the music there.
Okay. What we have to prove now? Let's see. There is something that might be clear, but it's not uh, too clear why it is true, which is there's some theorem 1.2. We talk about some three different statements, but we will make them and one theorem, which is a like it's like consists of three parts. So when I multiply zero with a vector, is clearly is a zero vector, and if I multiply a negative a, well, this b, a negative a with my vector is the same as I multiply is the additive inverse of a v is the same thing as what a times the additive inverse of v. And the last thing is if I have some scalar c and multiply it with the zero vector, I would get the zero vector. Okay, let's prove those statements. Well, this is a vector, this is a vector. Uh, let's see. The zero is just a 1 plus minus 1. Okay, and with our axiom number, I guess 7, which is AS7. You could check if I'm wrong. Is it AS7? Okay, I guess it is. Then we could distribute AV1 V plus negative 1 V, and we got into something that has a little bit problem. What is negative 1 times V? We don't know, right? For that, we have to reach that negative 1 V has to reach negative V, and I will make it this as a star. If we have to prove this, we could easily reach, okay, this is a zero vector, but we don't have it for that. How to reach this fact? Okay. To reach this fact is something similar to what we have done. If you have the zero vector, uh, which could be written. Okay, I guess I will make a circular reasoning in my mind because what I will prove now needs something in the next theorem, and the next theorem is this idea. For that, I will make circular reason. For that, okay, we will not use this proof. To not fill in this circular reasoning thing, I'll do another proof. Okay, 0 is just 0 plus 0 times our vector, and with distributive laws, this is 0 plus 0. And with theorem 1.1, 0v is just equal to the 0 vector. This is more easier because we could just write this as 0v plus the 0 vector, because anything times plus the 0 vector is the same thing. For that, we could do this thing with theorem 1.1 and we reach what we need. Okay. And to reach B, the first thing is easy. For negative A, just negative 1 times A, because it's already defined in the field. That additive inverse is like that. For that, we would steal this from them, that negative A of V is just negative 1 times A V, and this is would be just negative 1 firstly. We'll have to make like parentheses like that, AV. Okay, and we need another property, which again we'll leave this like that for a little bit. We won't reach that if we have like 0 vector and you break it in two parts, 1 plus -1 v, and this is exactly the same as a zero vector times v, which could be written as how to write it, v plus the negative v, and this is times v, which is 1 times v plus the -1 times v. Then this is equal to this, and actually 1 times v in our axiom is already equal to v. For that, negative v is equal to -1 times v. For that, we could use this fact in this. For that, this is just negative AV. Okay? For that, what we have proven here, that this is this. And we could do a similar thing that we flip this, and we would get the same thing. It's like, how to write it? Negative A V is just A -1 V, and we could take -1 firstly. With V, and this is clearly what we have proven here. This is just negative V. For that, our P is true. Then what we want to prove, lastly, that we multiply it with any constant, we get the zero vector again. Let's try that. We have C times the zero vector. We could write it as something like what I wanted to remember the best one was. We could break the 0 to v plus minus v and distribute the c, and would clearly get it, I guess, if we c as v plus the negative v, and we multiplied the c with cv plus c negative v, which was our p, what we already have proved, that is cv plus negative cv. And this is the additive inverse of this, then this would be 0 vector. Okay. Is this proofs are clear? Or just some steps that is not clear? I have to go to the script and check what people say. Yeah, well. Please use a set of functions like anti-Euler matrices and polynomials. Yeah, well. In the general case, so that we don't have to worry about how operation is defined. We browse the statement, which is really important statements, and let's go to the section 1.3. Finally, section 1.3. The section 1.3 is talking about what is a subspace. If we took a subset, which is a vector space, and we took a subset of this vector space, does it has to be a vector space or not? Well, let's take some example. Like if we have some R2, which is this is R2, and I took subset, which is this line. I have to get it in the origin. This line, which is all the vector at this line, and another line, which is this. And what we want to check that this subset would act like our vectors, which if I added this vector and this vector would give me a thing in our subset. So it's called this thing and this thing as set W. For that, if I added this vector and this vector, we got this vector. But this is not in W, then it doesn't have to be a vector space. For that, we have to check if we take a subset of some vector space that this subset is a vector space to be a subspace. For that, not all subsets of the vector spaces has to be subspaces. Is this clear? Okay. Then let's write a definition of what is a subspace is. Well, definition, a subset W of a vector space V over the field F is called subspace when it has the same like operation, like the addition operation we already defined in the V is the same addition operation we will define in W. For that, W is a vector space over the same field and the same operations of addition and multiplication. Well, there's some axioms that clearly are straightforward we can get from what we have from F. Since W is a subset from V, and we know that X and Y, we could flip it out with commutative rule because they are in V, and they are also in W and in V. For that, the X and Y in W is also commutative and also associative and also has the properties of what I say, then as other properties of like it could be we could multiply it with a scalar, but it doesn't have to be in the subspace, and we will show why. For that, we have to check exactly 4 points that if we have it in our subset, then it is a subspace. But the other axioms just follow exactly from what we have said. Another axiom that doesn't have to be proven one time is our x is our x. Another axiom is a distributive, and the one which is AB, and we take the semi-distributive or associative, I would say, with multiplication with the vector. This is all true from V. For that, we don't have to prove those. For that, we have to prove some things, which is the x plus y has to be in W if x in W and y should have written like that. And also there is, if I multiply it with some constant, it has to be in our subspace, and 0 has a 0 vector, and we have inverses like for all x in W, there exists uh, y where in W where x plus y equal the 0 vector. Okay. This statement is a little bit redundant to this statement because we have proven that -1 times x is equal to -x, which is the inverse of x. And if we have proven that any scalar, if we multiply it with x, would be in W, then this would be also in W. For this, we don't have to prove again, which is for x, there is an inverse for this x. For that, what just we need to check it is closed under addition, closed and under multiplication, and our 0 vector is in W. And what we want to prove now is that if it's a subspace, that the 0 vector of V is exactly the same as W if W is a subspace. And to prove that is totally easy. Let let us define uh, 0 dash as the vector space 0 vector 0 vector of W. Then for every x in W, x plus 0 dash is equal to x. But also x is in V, then x plus our old 0 of the vector space V would get us x. Then x plus 0 dash is x plus our old 0, then this 0 has to be exactly as the same as 0. Then by that we just have to check x plus y is in W if x is in W and y is in W, and cx is in W if x is in W and C is in our field. Did I write this right? Yeah, I didn't write that C is in the same field, but it has to be. And 0 is in W. Is this clear? Okay. Let's try some examples. If we have some R2, which is something like that, and I took a subspace of all barrels of some vector. Let's say this is V, and I want to all the vectors, which is here. Let's call the set W is all the set. Okay. TV, where V is is some A1, A2, and T. To make it like a line, T is an R. Then W is a subset of R2. We have to check like that if I add a V and a V, then or another like TV, I should say like that I would get something on the line because it's just multiples of V. Or I added the V, like SV plus TV, I got like an AV, which is also in this subset. For that, adding is closed, and multiplying is also closed because it's already defined as multiplication of the R, and R is our field. For that, if I multiply it with R, I will get something in the subset. And if I set t to equal to 0, I got 0 times our v, which is proved that is a zero vector, for that zero vector is in our w. For that w is a subspace of R2. Okay. Let's take examples from the book about to define some addition and multiplication of a vector space and take some subset of it and check if it's uh, a subspace or not. Let's go through some definition of something to see to use it in our proof. What is a transpose of a matrix? Well, if I have a matrix A with entries I, J, and I make it like there's a function T, which is we will make it together as a mapping, which make it maps to AJI, which is flips our matrix totally. For that, it takes entries or from set in XM, this field, and map it to MXN of the field. And if we have a vector like that, 1, 2, 4, 5, 9, 11, and we took the transpose of that, we would get something like that. 1, 5, 2, 4, 9, 11. Okay. And we could say that if the matrix and we take its transpose and we get the same matrix, it is symmetric. Why? Because it's symmetric over the diagonal, I would say like that. I don't know how to spell symmetric. Okay. I guess it's like that. Metric. I don't know if it's right. Over the diagonal. Let's go symmetric. And for that, if something like that, 2, 1, 1, 2. When I take the transpose, I just get the same matrix, which is 2, 1, 1, 2. For that, this matrix is a symmetric matrix. Let's talk about all the matrix with this property, and we have to realize a matrix has to be symmetric, then it has to be a square, because you could never have the same matrix if the rows and column is not exactly the same. For that, let's check matrix says m times n over the field and took the subset of the symmetric matrix and see if it's a subspace also. This is clearly a subspace because we have seen that all types of matrix where field entries is a vector space. For that, if I took any number of rows or columns, it also be a vector space. For that, let's take from this a subset, which is all square symmetric matrices, which is from okay. I have should written n times n, but it doesn't matter. Let's see if our addition operation is closed or not. But we have to check some really good properties to use it. Is that if we take in any matrix, which is assuming that the CA plus, let's say this is D, B, and we took just transpose, we assume that A and B has the same columns and rows. Does this equal to CAT plus DBT? Well, in the book, it doesn't prove why is this true, but you could prove it if you want to check that this thing is true. And we could have written like IJ to say that is what I talk about is, or it doesn't matter. It's exactly equal. For that, to use this property, let's check that if I took a matrix A and a matrix B, let's say A is equal to AT and B is equal to BT, we want to prove that A plus B T is also equal to A plus B. Okay? Well, A plus B, we will distribute the transpose, something like that. It would be AT plus BT, and we would get A. This is clearly from above is true. For that, we could just remove the transpose and we would look like that. And this is true, then it's closed under addition. And similarly, we could do something like that. And we would take the transpose and we reach out that C is 80, which is TA. Then it's closed under addition and closed under scaling. And clearly it has the zero matrix because the zero matrix is symmetric in some way because it's all if you transpose the square matrix of all zeros you will get the same the zero square matrix. For that it's also symmetric. Then this W, let's say, is a subspace. Okay, it's not CA plus. Okay, okay. I hate you. I will not correct all of them. Okay. This is how I write T. Okay. Let's take another example. We have in section 1.2 define B f of all polynomials with coefficient of this field. And we could take a subspace of it, which is P in F, to be all polynomials with at most n and nothing else, which is clearly a subset of Bn because Bf has all the powers, but this has only powers of n or less. Okay. And clearly, if you take some polynomial from B of n, let's call it f, which is has at most degree n, and another function which is n or less, f plus g has a degree n or less, has to have a degree n. Sorry, uh, and in if you multiply it with a field, the degree is the same, and you have the zero vector because it's -1, and -1 is less than our n has to be because n is we starting from 0, n is a natural number. For that -1 is less than n. For that the zero function, which is this, exists in all of our P and F for any n. For that B of n of F is a subspace of BF. Mm, well, this is the main thing that I don't know. Should we take another example or should we skip to the theorem 1.4 and give this example as a exercise for the next week? What do you think, Vincent? Yeah. We have only one theorem to prove, and we would finish the section. And all what we have left is just examples for what a subspace could be. For that, we haven't left anything. This theorem is easy to prove. For that, we could prove it in 10 minutes, hopefully. If we have C, which is collection of subspaces of V, let W be the intersection of all these subspaces, then W is also a subspace. Well, to prove that, given some X and W in our W, if we have added X plus W, well, X plus W is in our two subspaces. For that, it has to be in W. And to make this more clear, what is this true, I could get like some example. If you took this is a subspace of R2, and this is also a subspace of R2. And we took the intersection, which is the zero vector, and clearly the zero vector is a vector space. Because all axiom, if you want to check, 0 plus 0 is also 0 if it's closed. 0 multiplying by 0, you get 0, or multiplying by 1, you get a 0 vector. Versus identities exist, the inverse of 0 is 0. For this example of intersection would follow what we are saying. And here, if it's also x plus y is also closed in our addition. Okay, because x and y is in all, like, for example, if w is equal to v1 subset or intersection of v2, and we know that this is in this and this is in this, because v1 and v2 is subspaces of v. For that, this thing has to be in w also. Okay, and the same thing is for if we get some elements of the field and multiply it with x, it has to be in w, because with the same intuition, it's also true. And finally, how much you have to take intersection, the zero vector is in all of them, then zero vector has to exist in our W. For that, it holds, that is, all intersection is true. However, we could think about the union of all subspaces. Is it a vector space or not? We could give some counterexample, which I already have given in some kind. if we take this line in R2 and this line, and if you took the union, which is this set with this two of vectors, which is all the scaling of this two, you could get out this vector, which is not from this or this, and could be added from this vector and that vector, and we would get it's not closed under addition. For that, it not doesn't hold for union. And I guess this is the end for our like meeting, and I would like give some exercises on what we have to solve, or examples and exercises what we have to look at. I will send it in the announcement and to look it over this week. And sorry if I was not clear about explaining some stuff, and I was a little bit slow in explaining, and I had a lot of time to explain this concept, but I wanted to make it to be clear as I could.
Now I wanted to just step in here and say thank you very much, Mina, for hosting the first presentation. It was very nice to have that. If you're okay, Mina, to stay for a little bit, I'm going to kind of close down the Twitch side of things and we can do a debrief, maybe with some of the other people who are going to be presenting in the Algebra group. Does that work for you?
Of course. Of course.
Okay, fantastic. So for those of you that are just coming in and watching, I have started to post some problems up for you in the simple server. We'll kind of direct your attention over there. If Mina has any other questions that he would like to add, he can do that as well. So thanks again for coming and hanging out with us for a couple hours. We are planning our next presentation in the simple server to the best of my knowledge, and that will happen on December the 7th. It's going to be a little bit later because Cluster is going to be presenting for us. It's going to be a little bit closer to, I think, 7 or 8 o'clock p.m. Pacific time. Okay, if there's any kind of final thoughts, Mina, I will leave the floor to you, okay?
I hope this lecture to be interested to present themselves. Me as like I wouldn't say like not good at English very much, but I try to be brave and try to explain and understand what I'm studying. We're doing this reading group to like motivate each other. Don't take it like stressful. You have to follow up and to be serious about what you're studying, but and this is just like a thing to help you to go through that, and we will do a lot of stuff rather than linear algebra. You should check out our simple group. So
all right, amazing. Thanks again for Mina for hosting. Thanks to all of you that came along to Twitch to check us out over here. I'm going to be shutting the Twitch redirect down. We're going to be posting this video live on YouTube, and the link is going to be posted for you in the simple server, and we'll probably port that over to the elements as well. Yeah, so Fem, you're correct. We covered up to about section 1.3 from the textbook. And I'll be back with you guys. We'll be doing some abstract algebra tomorrow night. So I think Zach is on. We're going to go ahead and just raid over into Zach. That's going to be e to the 2I pi, and we'll see what Zach is up to. All right, thanks again, everyone, and we'll see you tomorrow. Next week, December 7th, is when we will host our second lecture session for linear algebra. Be on the lookout for announcements for that coming this week.